Well, welcome everyone, and welcome to the Water Exchange Speaker Series. I'm Howard Newkirk. I'm the director of the Water Center at Penn, and the Water Center is really delighted to be co-hosting this program with our colleagues at the Vagelos Integrated Program in Energy Research, or more commonly known by its acronym VIPER. We have a great program for you today, discussing opportunities and innovation at the nexus of water and energy. Our guests are John Vos, who's the co-faculty director of VIPER, who will be moderating a panel session with Christopher Gasson, managing director of Global Water Intelligence, and Paul Cole, director of planning and research at Philly Water. Before we start, I want to let you know that this event is being recorded and it will be posted on the website and social media for anyone who's not able to listen to the program today. Next slide. For those who may not be familiar with the Water Center, we are an applied research center focused on solutions to urban water challenges. We offer a series of programs and publications and welcome anyone who is interested in learning about water and wants to collaborate with us through projects, research, or programming. Please reach out to us via our website, social media, or send us an email. Next slide. VIPER is a dual degree undergraduate program that prepares highly talented students to advance sustainable energy science and technology through interdisciplinary approaches and cutting edge research. You can learn more about VIPER by visiting their website, contacting them by email, or following them on social media. Next slide. Our program will begin with a brief overview of what we mean by the water energy nexus. Christopher and Paul will follow with brief presentations, followed by a panel discussion that's moderated by John. The remainder of the program will be open to the audience for Q&A, starting with 2 questions by students from the VIPER program, Michelle White and Andy Eskenazi. We really want to hear your questions. Please send them to us via the Q&A icon. We'll get to as many as we can. And let me begin with some brief introductions. More full bios are available on the program invitation. Professor John Vos is Penn's Patterson Professor of Chemical and Biomolecular Engineering, where he chairs the department and co-directs the VIPER program. Professor Vos has authored over 300 publications that have appeared in scientific journals and holds 7 US patents. John received his PhD in chemical engineering from the University of Delaware and joined the Penn faculty in 1989. Christopher Gasson is managing director of Global Water Intelligence and co-founder of the Global Water Leaders Group. Global Water Intelligence is the leading source of business information and data relating to the international water industry, while the Global Water Leaders Group is a not-for-profit network of water utility CEOs committed to improving the performance of the water sector. Christopher is a graduate of Oxford University with a master's in politics, philosophy, and economics. Paul Cole is a professional engineer with 30 years experience in water utility research. He is currently the director of planning and research for Philadelphia Water. He has been a co-PI for several multinational research projects related to turning wastewater into a resource. His projects include sewage thermal energy use, a biogas cogen facility, a solar installation, and the investigation of food waste co-digestion and generation. Paul is pursuing his PhD in civil, architectural, and environmental engineering at Drexel University, where he also serves as an adjunct professor. Next slide. And the Water Center at Penn is what we do is we find local solutions to our global water challenges. The watersheds that support these challenges and the communities that rely on them, our focus really is on community, equity, science, resilience, and justice. Next slide. I've been talking for quite some time about how water is really focused on adapting to climate change and adapting our water systems to disruptive climate change. We're recognizing that this is going to require disruptive change in how we communicate, plan, design, fund, construct, and operate the next generation of resilient and sustainable water systems. Interesting, however, is that what I've been learning more about recently is about how the water industry is also a leader in how we're going to mitigate climate change and how we're going to control greenhouse gases. Next slide. And the water industry is really transitioning at this point to water utilities becoming what we call anchor institutions, institutions that are working for the benefit of community. In the past, we worked very much as a service industry where we provided drinking water and we took your waste and we treated it and sent it back to the river. Now we're looking at the full integration of economics and job integration and convening and collaborating with community and others, and really looking at the entire spectrum of public health enhancement and understanding how the water systems integrate with other systems. On the right-hand side is just a basic range of practice for starting at the top level, which is a base level, which is what we were, which is just seeking value within our utility operations. But as we proceed as an industry, we're moving more towards these advanced practices. We're creating co-benefits for the region or for the water sector, or in some cases for the world. Next slide. So what is the water energy nexus? Well, at a very basic level, energy needs water. They need it for cooling, thermoelectric, they need it for hydroelectric, refining and fracking, biofuel production, and other needs for water in the energy business. And in the water business, we need energy to treat and pump. It's that simple. What's interesting is that the largest user of water, the largest sector user of water is the energy industry. And the largest user of energy is the water sector. Next slide. So wastewater, is it the new oil? Is it something that looks like this when it comes in and then becomes something that is of great value to us? So in the past, we've just discharged, we'd clean the wastewater as best we can, and we'd send it out to the river for where it would return to nature. But now we're recognizing that there's a lot of energy hidden in the wastewater. Most of it, from the top right corner, is thermal energy, but there's some hydroelectric and some chemical. And for the hydraulic energy, there's both potential and kinetic. And that's basically, it's so simple to just think about it as it's water that's elevated and it's flowing, so it has energy in it. It is warm, so it has thermal energy. And it contains organic materials which can be broken down or reconstituted, and that's the chemical energy. So what we found, next slide, please, is that if you can recover the energy from the wastewater process, that you can have a lot of energy left over for sending back to the grid, to the electric grid, or to use for other purposes. This simple diagram just shows a small amount of wastewater and the amount of potential energy can produce. In this example, it's 2 kilowatt hours. There's only 0.4 that's needed to treat the wastewater. So it leaves you with 1.6 potential energy for other uses. And that energy, that's the potential that we have here to really seek out and pull the resources out of the wastewater and reuse them. Next slide, please. So wastewater facilities have the potential to produce the energy needed not only to treat our water, but to help heat and power the cities that depend on them. Next slide. And our goal, and this is where I'm kind of blown away, because we've been talking for years about net positive energy. How do we produce enough energy to not only power our facilities, but also send back out to the grid? But we're now talking about net neutral greenhouse gas releases. And with that, I'm going to turn this over to Christopher, who's going to talk more about this. Christopher.
Hi, can we have my slide? Yeah. So we've done a analysis here of the sort of global energy consumption of the sort of water utility sector, sort of looking at all the sort of from the sort of resources side all the way through to wastewater. And you know, you can see that there's quite a lot of pumping going along in terms of the water resources and also in networks. A particularly sort of intensive thing is the sort of desalination area. That's you know, obviously because you know, you've got to overcome the sort of laws of thermodynamics to take salt out of water. And as I mentioned here, it's, you know, the total the energy consumption of the desal sector is about the same amount as the electricity consumption of Chile. Now, it sounds very daunting, but actually one of the good things about desalination, it tends to happen in those parts of the world where it's very hot and sunny and good for solar power. And one of the things which has really been driving the desal industry in the Middle East recently has been, you know, ultra low cost solar power for desal, which has sort of essentially cut, you know, maybe a third off the cost of desal over the past 3 years. Then we got the sort of the wastewater side. You know, here when we get around to the sludge, this is talking about tons dry solid rather than volumetric cubic meters. So, you know, you don't sort of assume that all this sort of sludge is that energy intensive on the same scale that these other things are. And as you can see, we reckon it's about 3 point, or at least the EIA reckons about 3.7% of the total global electricity consumption. And then looking at the, can we have the next slide? Looking at the sort of ideas that people have for reducing that energy consumption. You know, obviously the water resources thing, I mean, it depends on where your resources are coming from. So it's, you know, some things obviously require pumping and such like. We have, you know, essentially optimizing the sort of energy use in the water networks, you know, making sure that you know, using digital technologies to improve efficiency in sort of water treatment, getting the consumers to sort of manage demand better, because if water is energy, then using less water means using less energy. We've got the sort of similar sorts of things in the wastewater side, and then, you know, this sludge to energy thing, which I think Howard alluded to, and, you know, different things that one might do in the wastewater treatment side. But this is very much in the sort of the, you know, the treatment and distribution train of water. One of the, you know, there are other areas where utilities use or produce emissions, such as in their fleets, you know, i.e. their trucks and so forth. And, you know, we're seeing people move to electricity or indeed biogas from their sludge plants powering their fleets. Can we have the next slide? This is sort of looking a bit more at the sort of wastewater story on the emission side, because on the wastewater side, you're not just dealing with the you know, the emissions related to the energy consumption. You're also dealing with the emissions related to the you know, carbon dioxide, methane, and nitrous oxide coming out of the wastewater process. And you know, methane and nitrous oxide are these sort of super greenhouse gases, which have a much bigger impact than anything else. And so, you know, dealing with wastewater properly can have a huge impact on greenhouse gas emissions. You know, particularly dealing with sort of nitrous oxide, possibly by you know, better sort of aeration in the wastewater treatment process, and, you know, dealing with methane, or indeed using the methane for generating electricity rather than just having it going out into the atmosphere directly. I did a little sort of calculation here, looking at the sort of current energy yield from sewage sludge. And we think that at the moment it's about 7.4 terawatt hours coming out of the total amount of sludge where anaerobic digestion is used. And we think that actually just using the sort of state-of-the-art technologies, that could be increased fivefold to get to 37.5 terawatt hours. And that if we could actually deal with all of this, the total amount of sludge currently treated in wastewater treatment plants with the sort of cutting edge technologies, we could really make a huge difference. And then beyond that, you have all of the sort of wastewater which is not collected in wastewater treatment plants, but goes into sort of latrines or septic tanks and so forth. And that again is a sort of huge potential resource. And can we move to the next slide? This is, I mean, this here is something where from Amsterdam Waternet in the Netherlands, where they were looking at, what are the things that we can do as a utility to, reduce the emissions by the largest amount, and what are the what's the cost and benefit of those activities. So these things are all things that could be done, which would actually save money, or produce a sort of positive cash flow, as well as reduce emissions. And the things which are in blue are things which the utility itself could do, and the things which are in these other colors are things where it sort of needs to work with others in order to deal with this. So, for example, aquifer storage for cooling power for data center. That's they've got to work with the data center in order to do that, or with the struvite recovery. I think that they needed to get a partner actually to do the turn that into money. They can't just take the struvite out and say yippee. They've got to find somebody who's going to actually buy it. And then they've got these what's this H is sort of getting that sort of heat exchangers in the showers and so forth, and which again, much more difficult to get as a utility to get that sort of thing to happen. But I mean, I think that one of the things that we're looking at is trying to sort of understand what this cost curve is for utilities globally, or possibly just on a regional basis, because each utility essentially has a different cost curve. And I think that one of the things which we find exciting about this is when people look at this, they can see that this is something that engages the public. The public are concerned about climate change. They want their sort of utilities to be leading on all of this and so forth. And it's also something which will change the way that utilities work. And we see it, actually as a potential catalyst of that transition, which Howard was talking about, of utilities in terms of their role over time. So, I mean, that's sort of plugging into the big picture, and that's my presentation.
Thank you, Chris. I'm Paul Cole. I'm going to talk to you more about the water energy nexus from the hands-on perspective, the practical. Chris gave you a very good overview of global systems. Very informative. I'm going to start with this slide, which is lovely. And by the way, there's the small pictures, but I want you to pay attention to the first one, because I'm in that first one and I'm standing next to Howard. And so it's a lot of fun for me to show this one at this particular conference, because Howard and I are both in the same picture. But anyway, that's the ribbon cutting of the biogas cogen facility. And this is my let's brag on PWD slides. So then the next one is that we worked with the Department of Streets and the incinerator manufacturer of food waste disposers and ourselves. And we did a pilot study where we gave out 100 food waste disposers to 3 different areas of the city. So we gave out 300 food waste disposers and we tried to see if we could see if there was less food in their waste, and there was. The third on the right is a just simple solar system that the Philadelphia Water Department built. It's at one of its waste water pollution control plants, which I often refer to as water resource recovery facilities, but it's at the Southeast Water Resource Recovery Facility, and it's just a solar farm, but it's producing electricity, about 300,000 kilowatts a year. And the bottom picture is was given to us by the airport. The water department made a contracted with the airport because they were trying to get rid of their aircraft de-icing fluid, and aircraft de-icing fluid has an extremely high demand of oxygen. So if you feed aircraft de-icing fluid into the front of a wastewater treatment plant, it really consumes a lot of oxygen and consumes a lot of electricity in providing enough oxygen for your biomass to do that. However, if you inject that ADF, aircraft de-icing fluid, directly into an anaerobic digester, it really gets consumed very quickly. It produces no mass, negligible mass, like, far less than 5%, and it just energizes the system. So these are the sort of showcases of the Philadelphia Water Department over the last 10 years. If you'd advance the slide. This, back in 2014, 2015, the Water Department had a vision, and I kind of want you to keep that in mind. We thought about an eco-industrial complex. And so we were really, and again, going to tip my hat to Howard, we were very forward thinking. This is a like infographic, and the darker brown circle is sort of the boundaries of the water pollution control plant, which of course here we refer to as a water resource recovery facility. And it turns out that we can get food waste into the plant through the sewers. And a thing I always add when I talk about food waste disposers is that food is 70% water. We, people, are 70% water. The point is, when you grind up food waste and send it to the sewer, 70% of that weight is water. We also had hoped to get a commercial food waste diversion program going where we would process the food waste and also inject it directly into the anaerobic digesters. Again, at the facility, we built a biogas cogen facility, which generates electricity and heat. And that heat is returned to actually keep the anaerobic digesters warm. The airport is over on the right. You see that little thing? The aircraft de-icer fluid goes in, and that goes into our. And so then the rest becomes sort of the next gen. The next gen was, we could grow algae, and algae could be the source of, food for agriculture. It could be there's also a way to run an anaerobic digester to produce volatile fatty acids and stop the process there and use those volatile fatty acids as a bio block for future refinery work. Not pie in the sky, but very advanced. That's it. So you can move to the next. We had a lot of vision, but you can move to the next slide. We were thinking a lot about that. Now here comes a great procedure that you should keep in your mind if you want to save money. The city of Philadelphia, maybe 10 years ago, maybe 15 years ago, decided it was going to reduce the amount of cost of its energy while hedging for future energy prices. So this is old data. It's up to 2020, and what it shows is that we buy electricity for 1 year out. So the city of Philadelphia buys about 80% of electricity it thinks it'll need in a year in advance. And then it buys the amount of electricity it thinks it needs, about 50% of the electricity it needs 2 years in advance, and about 25% of the electricity it thinks it needs 3 years in advance. The reason for this is that you start buying electricity on, you don't get a guaranteed price, but you hedge it. So I won't get into too much of the actual mechanics, but the city of Philadelphia, the airport, the water department, and the general fund, which includes lighting and all sorts of things, street lighting, its office buildings, have contracted with a firm that buys our electricity from the RTO, which is the Regional Transmission Authority, which is called PJM, Penn, Jersey, Maryland. It's one of the most, it's a very large and robust regional transmission authority, but we buy electricity on the wholesale market. We buy it and enter into these contracts. And this graphic is to show how we do it. To orient you more to this graphic, the top line is the last year's electric usage we actually had. This is how many megawatt hours we've used. The bottom line that's a mirror of it, just a little bit low, is the low end of the hedge. We never buy 100% of the electricity we need, because if you don't use it, you've already paid for it. So that line represents about 90%. That's the maximum of our hedge. And the white line is the minimum hedge. And what we do is we try to keep our energy purchases in between those two things. And it's very effective. If you go to the next slide. Again, I'm telling this a little out of order, but when we built the biogas cogen facility, we did our analysis in 2008. We thought a lot of our electrical costs were going to go much, much higher. So we actually did this analysis twice before we pulled the trigger on the biogas cogen. However, after building biogas cogen, the electricity didn't go up, it went down. So we did another analysis. So this is the third analysis of what we thought would be the price of electricity. The reason I want to show you this is even as far back as 2016, we thought the cost of electricity would be going up to about 10 cents a kilowatt hour. The other thing I want you to notice in this graph is that there's a red line and a blue line. The red line is, we thought that would be the price of electricity, about 9 cents a kilowatt hour, just anyways. Now, if you recall, Barack Obama was president and we had a clean power plan. So the US EPA was trying to decarbonize the electrical grid in an accelerated rate. And we thought that that would add about 1 cent per kilowatt hour. Again, you go to 2040, 2041, those lines become very close together because we think everyone's going to be doing it by then anyhow. The two things I want you to notice is that we really thought the price of electricity was going up, and we thought the clean power plan would actually accelerate that. And I think that's a good thing. The third part is leadership's important. I'll talk about that at the end. And the fact is that we didn't act on that has really changed the price. Next slide. Here's some practical implications. In 2014, we were paying 6.87 cents a kilowatt hour. In fiscal 15, 8.5. In fiscal 16, 8.2. And then you can see it going down and down. And the percentages underneath are just simple math, but I like to show that simple math. From fiscal 14 to 15, the price went up by 20%. From 15 to 16 went down by 4%. From 16 to 17, it dropped by 41%. Now, this saved the water department, the city of Philadelphia, and the airport a tremendous amount of money. In essence, 40% off their electric bill. Very effective, very helpful. The line below that is how much electricity was produced by the biogas cogen facility. Now, there's various things that I'm going to stop talking about that, but basically the next line is, what was the avoided cost of this facility? So when we produced electricity, we produced in fiscal 15, 33.8 million kilowatt hours. And that was worth about $2.5 million, $2.8 million. You go all the way to the right, fiscal 20. So it's about the same amount of production, produced a little bit more, but it's the same amount of production, but it's only worth $2 million. So the facility's still running. It's expensive to maintain and operate, and its value as opposed to going up has decreased. That's killing us. That's a long way to say we've sort of shot ourselves in the foot. So next slide. Just want to let you know also that the water department has demand curves on the other side. This is our demand curve. It's larger on the shoulders and lower in the middle. That's exactly the opposite of your normal demand curve, and that's important to help us buy electricity. Next slide. I already talked about this, but leadership, and I put Greta on here because I really think that Greta's making a difference, and any opportunity to say, go Greta, I'm going to take it. We do need leadership. The reason we were able to build biogas cogen was because the mayor and the Office of Sustainability really was helping the water department be able to do it. And I put political cover. They could provide political cover. What we really need is a carbon tax. Another side note, the value of water. If water is going to be used as a societal element, which it is, and I believe the Water Center talks about this, continuously, is that we really ought to consider about what we're paying for and how much it's worth. And that's it. Thank you very much. And I turn it over to John.
Christopher, Paul, thank you very much for those very interesting remarks. I'll try to have a little bit of panel discussion here. Maybe I can get the ball rolling by just sort of throwing the question out to Christopher and Paul. So especially in Christopher's presentation, you talked about greenhouse gas emissions and methane and NOx being particularly bad actors. So just what types of technologies are needed to sort of reduce greenhouse gas emissions on the wastewater treatment side of things that we're not currently already doing?
Well, I mean, I think that this is one of the things that actually we're not doing it. I.e., if you look at the world, you know, and you look at the Sustainable Development Goals, you'll see that the biggest miss is on what we do with our you know, fecal sludge. I mean, that there's no, you know, sewers and wastewater treatment plants only reach a minority of the population. And, you know, not only that, you know, the way that fecal sludge is managed in places where they don't have sewers is really quite terrible. And you get, that means that there is you know, a huge amount of methane going into the atmosphere, simply because you know it's not just a public health thing. I mean, it's interesting that you know sewage is something which you know it's really a sort of human right in many ways. You know, you should be safe from your own waste, but it doesn't work. You know, the numbers don't seem to add up, and this is why I think the whole sort of climate change thing could actually be the catalyst that actually delivers change. That you know, when you look at it through the climate change prism, it's absolutely clear that you know something's got to be done about this. And this, I mean, I feel quite strongly that the solution is actually emissions trading across borders. You know, i.e., if you know, let's say utilities in the developed world wanted to offset their emissions against you know emissions reductions from actually investing in fecal sludge management in the developing world, that would have a huge impact. And in fact, I mean, you know, we're planning our sort of conference next year in Europe, and we're proposing to you know offset all of the travel to that, or double offset it, by sponsoring better fecal sludge management in Haiti, because you know there's a project there that which we can put money into, and we can see real benefits from that. And I see that is the sort of thing that needs to be happening.
So Paul, along those lines, are there regulations on emissions from like in the US on wastewater treatment plants?
I'm going to add one more thing to what you.
Yes, please.
There's a if you're doing a plant-wide you know, nutrient control. Chris talked about this, but you can use you know, optical sensors to determine what your DO is across a large basin. So you know, you can have you could just have set up cameras, or you know, fly a drone over it, and you're like, well, that's, but really, you know, just like, is my system really working the way it's supposed to? You can actually tell by looking at them. And that kind of technological advancement is available, but that the boost to actually watch your process is still nascent, it's still growing. Regulations right now, no, we don't. We do and we don't. The state of Pennsylvania is trying to join RGGI, which is RGGI, the Regional Greenhouse Gas Initiative, and we're having an internal political debate. If we do join it, then the greenhouse gas emissions of the plant and the control could be, if we can control them, could be traded on the open market. As large facilities, we do have to report our greenhouse gas emissions to the state and to the federal government through the Clean Air Act and through certain GHG. We're large enough to have to comply. But back to what Chris was saying, we have to comply because we're really, really big facilities. If you're a small facility, you don't have to. And not only that, if you're a centralized facility, you don't have to report anything.
So since we're focusing on energy aspects of water, this kind of, maybe Chris presented some of this as well, and Paul certainly touched on it. So what are the biggest consumers of energy in the whole water system? Is it pumping the water around? Is it on the treatment side? And sort of what are the low-hanging fruits, things that we can do now to decrease energy usage in these systems?
Chris, is it okay if I go first?
Yeah, you go first.
You've already hit it. I mean, I would even say fluids, you know, for a wastewater treatment plant, for water, like a pump, you're pumping water. For a wastewater treatment plant, you're still pumping a fluid, it's just air. So, you know, it's pumping, you know, the compressors and the water pumps are what cost the most energy. Howard showed a little medallion of energy, you know, and thermal energy is available. So I think that's the lowest hanging fruit. And clearly I'm spending a lot of time looking at that. But within a wastewater treatment plant, that 20% is anaerobic digestion. I do think that's another low hanging fruit because the conversion of chemical energy is a fairly easy, and you get a very high quality energy and a localized high quality energy. It's very much underutilized and the plant capacity there. And then you've got all these nutrients that people have been historically just distributing or discharging into the rivers. And if we could start collecting those, and what we've shown in the Susquehanna River Basin is that, you know, we make people do it and they sort of, you know, raise their fists and then they do it and they realize, wait, these things are valuable.
It's actually a net positive.
People do things differently.
Chris?
Sorry, I was just going to say that, you know, it depends on where you are in the world. But, you know, in California, there's an awful lot of pumping, you know, going on to get water, you know, to Southern California from Northern California or the Owens River or wherever it may be. And, you know, the flip side of that is places like, you know, Scotland and Norway have got sort of water resources up in mountains or in lakes that they can use as reservoirs, and they can actually generate hydroelectric power from that quite happily. And you know, there's a lack of geography. I mean, I'd say that undoubtedly the most energy intensive places at the moment are in the Gulf region, simply because they rely 100% on desalination, and you know that's energy intensive.
This has already been touched on a little bit, but what role is government regulation going to play in solving this problem? I mean, obviously, it's going to have to play some role, but is that a critical need, or is it going to be individual utilities doing themselves? You talked about it on a global scale. Depends where you are in the world, of course. Where
shall I answer that? I mean, I think that I mean, you know, what I look at is the different emissions trading schemes, and you know, whether water is in an emissions trading scheme or not in an emissions trading scheme. You know, if it is in an emissions trading scheme, then you know it's got to take this seriously and you know find a way of getting it reduced. If it's not, then you know who cares? Now, at the moment, water is only in the Korean emissions trading scheme. I think that it will, the next country to introduce it into their emissions trading scheme is actually likely to be China. You know, who knows about, you know, emissions trading schemes in the US, but you know, it's in Europe. I mean, it's not generally in these schemes. And so I think one of the things that we're actually seeing is, you know, national governments, you know, dragging their heels on this, but city governments, which are often, you know, a little bit more concerned about this, not least because they're most exposed to climate change in terms of flooding and sort of water shortages, are really pushing sort of harder on it. But they can only really sort of have, you know, essentially voluntary climate change sort of emissions trading things. And you know, furthermore, are the public ready to pay for the cost of carbon in water?
I'd like to add two stories to that.
Sure.
I'm agreeing completely. I think there's a tremendous role for the government. First is that as long as carbon's not part of the cost, then it's externalized and the utility won't pay for it. And on that vein, both New York State PUC and Pennsylvania State PUC were approached by various utilities to introduce, you know, renewable biogas, renewable natural gas into their distribution systems. And in both cases, the PUC ruled that they could not, simply because the biogas was too expensive. And their rubric is, we must protect the consumer. And you're like, well, wait a minute. If saving the consumers to have a viable planet isn't part of that, why isn't that? So the government does have a need to restructure the PUC to where they're allowed, because they really couldn't. They said, listen, even if we wanted to, we can't agree. It's just too expensive. And they said that people would pay for it. They said, anyway, I'm gonna stop talking about that. So that's it. We do need the government to rethink what structures these things.
But I think you make a good point there, in that, you know, cost is important, and it's important to the consumer as well, but you need to present what are the other long-term costs in terms of health and flooding and greenhouse gas emissions, those types of things. how you roll that in. I would say though, places, depends where you are. In the US is a good example, how people feel on this vary from California to the South and things. But I think maybe there's some hope in the younger generation that people are starting to take these things a little bit more seriously, taking a longer term view of things that we do really need to start worrying about.
Well, one thing I just add to that is that, one of the great things about water and why it can all happen is because water is right there on both sides of the equation. People might complain, oh my God, we've got to pay the price of carbon in water. But if the price of carbon in water is cheaper than the price of climate change adaptation, which also happens through water, if it's going to require building desal plants or long distance pipelines or whatever, if it's going to stop that expenditure, then paying the price of carbon is a logical thing to do.
Agreed. I think we want to have time for some question and answer period. So maybe we should move along to that. And I want to start off the question answer. We have a couple of Penn undergrads from the Viper program that are here today that are very interested in this subject. Michelle White, who's a dual degree doing biology and bioengineering, and Andy Eskenazi, who is doing mechanical engineering and math as his 2 degrees. And Michelle, let me open the floor up to you first. Now you have a question that you would like to ask our panelists.
Yeah, definitely. I have a lot of questions. So yeah, in Viper, the interdisciplinary approach has me constantly questioning how we can involve locals, community members, everything in energy solutions and sustainability solutions. So yeah, it's been great hearing about all the different global and local scales and approaches to the water nexus, the water energy nexus. So this is more of a question probably directed at the PWD, but is there currently or a plan to install a framework for local involvement in the wastewater treatment process?
Thanks, Michelle.
Yeah, that's a great question, and it's and Howard's biting his tongue because Howard wants to answer this question. So, this is an excellent question, and as a good question, it's kind of difficult to answer. We really want a lot of people to be engaged in what happens, because when you ignore it, you don't have any appreciation for what's around it. But at the same time, too much engagement ends up being this weird, how do you do it? To answer your question about food waste, I think you should consider food waste. And now I'm going to start talking about streets and various things. You should know that even when you watch TV or movies, someone says, oh, I don't like this food anymore, and they throw it in the garbage. I mean, you see that every day. I want people to stop thinking like that. Put it down the sink at a garbage disposal, or have yourself a composting bucket and compost it. Do not throw food away. Now, that's not how you interact with the wastewater treatment plant, but that's how you interact with your city. And things like that. I mean, even like separating your recycling, rinsing your recycling. Water is a great resource for making our resources in our recycling streams much more valuable. So there's all sorts of ways. I'm going to say, pay your bill. That's the best way. And demand from your public servants and demand from your leaders that carbon be part of it, that the state join Reggie, that greenhouse gases be discussed at city council meetings. That's how you do it.
Howard, did you want to chime in?
I think Paul answered it very well. I just, the community is extremely important, and there's all different sorts of community. And in a city like Philadelphia or many other cities, there are lots of issues out there. And the question for me is always, how do you, as someone who's passionate and worked their entire life in the water business, how do you balance that with people who are dealing with jobs, with education, with crime, with housing, and how do you put all that together? And I think, Paul, you started to answer that question, because you got to make things, you have to link things that the public really wants, and things that we as water nerds really want to do also, and put those things together. And I think your example of watching TV and throwing out food is a great example of how you can start to make those connections. And of course, at the other end of the spectrum are these young men and women in programs like Viper, who just like it's what I live for, is to see people who are looking to change the world and are building up the capacity to be able to do that. And so it's a nice combination, but it's, there is no public. There's a million different publics, and you have to deal with them in very many different ways.
Thanks, Howard. All right, Andy, let me turn to you now. Do you have a question for our panelists?
Absolutely. First thing I want to say, this discussion was fantastic, and there's a lot that I've learned about it, especially towards the end when we were speaking about internalizing the cost of CO2, just dealing with equity issues in there and making sure that low-income groups don't pay more than other groups. That's super important. But I'm going to ask my question related more to the side of technology. And earlier in the presentation today, we discussed that desalination process is a very energy-intensive process. But however, to mitigate those costs or that high usage of energy, it's more efficient to use it in in areas that have a lot of sun, for instance, because you can have a lot of solar panels in there, and that can help reduce the cost. But my question here is, what are some alternatives or current research that is being done today in order to make this process more sustainable, especially in the context of cities that, for instance, cannot do that? They cannot have like an array of solar panels in there that can help mitigate the costs.
I guess that, I mean, first of all, I mean, in most cities, there's as we saw with that sort of cost curve for, greenhouse gas emissions reduction, there's a similar cost curve for, water resources. And, desalination is, usually, to the sort of right-hand side of that. Similarly, things like, building, new reservoirs in places is also incredibly expensive because, real estate costs near cities is expensive. But the cheapest thing that you can do, the things at the other end of the thing where you actually make money from doing it, are, things like, reducing leaks, just making sure your thing is your system is more efficient. Somewhere in the middle, you have things like water reuse, where you're essentially valorizing water which is actually the most expensive water that you'll ever make, which is the wastewater. But if you're looking at the big picture, i.e. not just urban water, you're talking about sort of agricultural water and what have you. There are huge sort of benefits to be had from things like no-drill agriculture and rainwater capture and some of these blue-green infrastructure things, which actually provide benefits on which pay for themselves. So I think that there are some places which have very few alternatives. If you are in Dubai, there is nowhere you can turn apart from the sea. But if you are in California, there are actually quite a few things you can still do. I mean, and I think in particular, over the next decade, the big thing in California will be water reuse. I mean, the whole Hyperion water reuse project that they're proposing will be a revolution when that happens.
I wanted to add my 2 cents to particularly the California thing, because I got to see Professor Luthi, Stanford, present some information. It was just about this desalination, the idea of the energy intensity of a very specific decentralized water reuse program was a fraction of the energy intensity of a straight up seawater desalination plant. Even moving from the sea to the bay is an energy improvement. Moving to direct reuse is a much better idea, including capturing that sewage prior to it gets closer to sea level, because everyone who runs a utility knows about I&I, inflow and infiltration, and your sewers are not sealed pipes. And if you're anywhere near the sea, seawater flows into your sewer. So by the time your wastewater treatment comes around, you actually do have some salinity in there. But I agree with everything Chris said.
Thanks, Andy. Thanks, Michelle. We do have some questions from the audience. So I want to see if we can get to as many of those as possible. So let me move along to one of those. First question is, we've seen many fantastic examples of utilities transitioning to net zero coming from more wealthy countries. What recommendations or guidance do you have for poorer countries, third world developing countries that have limited financial resources, what types of things can they do to still have an impact?
Like sort of dive into that? I mean, it's one of these sort of very difficult things. I mean, I did a project for the World Economic Forum a few years ago, looking at how SDG 6 could be achieved and what the economics of it all is. And essentially, when you look at it, good water pays for itself. If you take into account the time cost, the health costs, and everything of having a piped potable supply to the home, as opposed to some distant unsafe source, it pays for itself, and that's one of the reasons why we will probably achieve the Sustainable Development Goal for water. Sanitation, however, the model really doesn't work. That sewers and wastewater treatment plants are immensely expensive. And what we discovered was actually, as if you take this holistic costing, where you're looking at the health costs, how much time parents have to take off work in order to look after children who are sick from waterborne diseases and so forth. You take all this together. The wastewater systems only, including sewers and wastewater treatment plants, only pay for themselves when you get to an income of about $3,500 a head, a GDP per capita. So in that, it's really in that sort of sub $3,500 per head area that we need to look at alternative solutions for this. Now, this is something which Bill Gates has studied, and he's come up with his omnidigester, which is a sort of sludge to energy or fecal sludge to energy system. He's also got a vacuum truck, which he's sort of designed to be sort of slightly powered by this as well, which in theory the numbers all add up. But the problem really is for the Gates Foundation is actually finding the sort of the counterparty to take this on and make it happen. And I think that, this is very interesting. I mean, we had, Michelle raised a question about, local participation. And, the Gates Foundation is probably the most opposite thing of a local participation that you can possibly imagine. But, what I think is probably true is if you can create something where the numbers add up, if you can come up with a model for dealing with wastewater in such a way as you're reducing the emissions and sort of capturing some of the energy, capturing some of the also nutrient value for using in agriculture and so forth. And if the numbers add up, it's likely at some point somebody local will get excited and start making it happen. But as I say, there's not really sort of wastewater sort of concerned agencies or local political institutions with this responsibility weighing on their head. And that's besides the economics, there's also the politics of the problem.
Paul, I'm going to have the next question will focus toward you. So one of the question is, so one of their slides showed the energy value of the wastewater, okay, and it shows 80% thermal. But not much was talked about how one is harvesting that energy. So what approaches, if any, are Philadelphia using or other places using to harvest that energy?
To sadly say Philadelphia is not doing this. I'm hope that we will someday. Again, being on with Chris is a lot of fun because really the cost of energy and heating isn't that much in the city of Philadelphia, but in cooling, I'm gonna stop talking about the economics of it. It is being done around the world. In fact, I noticed a question come across with Nick Meaton. He's a gentleman who now lives in New Zealand, but I met him when he was in Germany. There are companies doing it. There are companies that are out there mapping things. The Canadian government has required and mandated greenhouse gas initiatives. And in those provinces where they've been more aggressive, you see these petitions. The largest one that I know is called False Creek in Vancouver. And they literally have a heat recovery, heat exchange system on a pumping station. They pull the heat out, they run it through a heat pump, and they produce a heat loop, and that heat loop then heats an entire district. And that is, I could talk a lot about that, but the point is that it's being done. It is being done on smaller and smaller scales where we'll take an apartment building and they'll take the wastewater from that apartment building, putting it in a tank, and then they'll pull that heat out of that tank to make the hot water for the rest of the facility. Now, already that sounds scary. You know, it's like you're mixing my wastewater with my drinking water. The answer is no, that there's hydraulic fluid between them. They're not in the same vessel. They're not connected at all. But it really is about recovering that energy. And Chris put in a slide about, 20,000 sewer shower heat exchangers. You get into that level that right now those don't work. You can't get enough heat out of those to actually make them make sense, at least not that I understand. And so you need bigger and bigger, and the bigger you go, the more they make sense. But we're not even doing the big ones yet. So I'm very excited the US start doing this.
Thanks, Paul.
Just
Go
so
to
that the,
one more question here. Is it feasible and economical to feed wastewater treatment sludge into the new AD plants being built on the Eastern Shore, for example, to handle poultry litter?
There's a BTS project they built down there, and where all the rubber meets the road was political. Can you build it? Will they give you permits? Are you allowed to build? Are you allowed to do this with it? Will the town? Years of administrative state legislative work just to get the thing built. And most people don't know is you talk about the technology. It's almost never, ever a technological problem. The answer is yes. You could absolutely do it. 100% yes. Will you be allowed to do it? And it turns out that there's political interests that are opposed to it for various reasons. So the simple answer is yes, it can be done. It is being done, and we should continue to look at the advancement of anaerobic decomposition, not only for these food stocks and waste streams, but also as primary treatment. I think, and this is going to tip my hat to Howard asking this question, 10 years ago, but I think in 50 years, wastewater treatment will be much more anaerobic than aerobic, that we can get our waste streams strong enough.
And I believe that you can do this in Maine and California. I may be wrong. I mean, I think that California has actually done some quite interesting legislation on that, which is why Andrew Benedek has sort of got this Energia thing in Orange County, which will take almost anything that's caught there. So.
Well, I'm going to jump in here, and unfortunately, our time is just about up. And really, thank you all so much for participating in this program today, and to the listeners who submitted questions for discussion. I thought it was really a great dialogue that I personally really enjoyed, and I hope you did too. And the program has been recorded and will be available on the Water Center's website starting tomorrow. And there's also a feedback survey that is in the chat, should be in the chat as a link. And you'll also receive one via email, because we want you to answer it, to take a minute and fill it out and show us how we can improve our future programming. If you have any suggestions for topics or speakers you'd like to hear from, please let us know via the survey. And thank you all for an excellent program.
Thank you.
Thank you very much.